All right, so here on pages 6 through 9, we covered a lot of notes about ionic compound names and formulas. And for these notes, I would recommend you have a periodic table out. If you don't, you can maybe take a screenshot of my next slide after we get some charges on there, because these ionic compounds, we need to know our charges to be able to put together their formulas. And on Canvas, I have broken these videos into, or this one big long video, into separate parts. If you only missed a certain section, or if you want to revisit only a certain section, then you can just kind of jump to that section. You don't have to watch through the whole thing. I would recommend, if this is the first time you're going through these notes with me, that when I take a break in the middle between writing formulas and how to write names, that you also take a break to do some of that practice there, just so that you can make sure your brain is kind of on the right track with that one type of skill before we move to the other one. So, like I said, periodic table is our first priority. We need to know our charges to be able to write the formulas of ionic compounds. And we can reason through, like the first column has one valence electron, and according to the octet rule, they're going to lose that one valence electron to get happy and full with the layer underneath. And losing an electron makes us a +1 charge, but we really just need to be able to find that charge. So I'd encourage you to write this charge on your periodic table if it isn't already there. Remember, this charge applies to every element in this first column, from the top to the bottom. The second column has a +2 charge. Remember, these elements in the middle, we don't know their charge. They can actually have multiple charges, and we can't memorize all of them. So we skip over those. Boron's column has a +3 charge, but really it's only boron. Underneath that staircase, we have our metals starting, and those are actually transition metals, just like the rest of the D block, and they can have multiple charges. So we will talk about what's special and different when they form ionic compounds, but that +3 charge and all of the charges in a non-metal area actually only go as far down as the staircase. So I like to start with those positive 1, 2, 3s, and then I start backwards. Noble gases, that last column, have no charge. They don't form compounds. Our fluorines column is going to be -1. Remember, they had 7 valence electrons, so they gained 1 to get 8. Gaining an electron makes them -1. Next column is -2, and the next column is -3. And this is just what I remember. I remember to go forward in the positive direction. They're getting bigger, positive 1, 2, 3, and then starting from the end, remembering to skip the noble gases, these are negative, and they are getting more and more negative. So -1, 2, 3. So positive 1, 2, 3, -1, 2, 3. You have to have these memorized. Now, yes, technically they do meet in the middle at positive or -4, but these are almost like those transition metals where they can have multiple charges. Are they going to be plus or minus? I don't know. You don't need to be able to know at this level. So mostly what you need to remember and memorize is the positive 1, 2, 3 and -1, 2, 3 there. So real quick before we move into the rest of our page 6 notes. On page 6, we drew some ionic compounds and the formation of our ionic compounds. I just wanted to draw your attention to some patterns you might have started to kind of notice, especially with some of these last couple of examples here. When we had our, what do you notice about the charges compared to how many elements that we needed to have in order to form this ionic compound? If we look at these, you notice anything here? I think it's a little bit more obvious when I do another example. It was a little bit too long for our notes, a little bit too big for that space. But notice how when Al had a +3 charge, we ended up needing 3 sulfurs, and then sulfur with its -2 charge, because it gained 2 electrons each, we ended up with 2 aluminums. It's the same numbers, they've just kind of switched places. The charge on one element became how many elements we needed of the other element. And that's actually going to be the process that we use to write our ionic compound formulas, to say how many of each we need to have in a single compound. We're going to use those charges, that's why they were so important that we write on our periodic table, and we're going to do what we call cross, drop, reduce. So you see that there at the bottom of page 6. You can see this happening, and I'm going to walk you through these steps with this example here. So imagine that you're looking at a name, and we're going to talk about how to write these ionic compound names a little bit later, but they're pretty simple. They're mostly just the element names, aluminum and phosphorus. But just like with our ionic compound names, or sorry, just like with covalent, we change that last element's name to have that "ide" ending. So when I'm looking at something like aluminum phosphide, we're going to start by finding the element's symbols. So symbols of our elements first. So that would be like writing down Al for aluminum, P for phosphide. Then our next step is to find the charge of each element. So our charge of aluminum is +3, P is -3. And then we're going to go into this kind of three-step process: cross, drop, reduce. And I normally do my crossing and dropping kind of at the same time. And what that means is that I'm going to take these numbers, these charges, and cross them over and down. They need to become subscripts on the other element. And at the same time, as we cross the charges, we're also going to drop the signs, because we don't need plus and minus signs down here. These numbers down at the bottom tell us how many of each element we have, and we can never have any negative elements, negative atoms. So they're all going to be positive, and that means we don't have to write the plus signs. So crossing and dropping happens kind of in one step. We cross them over to the bottom on the other element. Here they were the same, so you can't really see that happening much. Then this last step is kind of special. It's reduce. We're going to bring that ratio down, divide these subscript numbers by anything, any common factor that they have. And when they're the same number, 3 and 3, then their common factor is that number, 3. If we divide each of those by 3, 3 divided by 3 is 1, and we still don't write ones in our formulas. So that's just going to become ALP. So that's what you see happening over here already in your notes. We're crossing, dropping, and reducing our charges. Now, more often than not, we're going to have different charges. They're not always going to be the same. So let's just imagine an imaginary compound XY, where X has a +2 charge and Y has a -4 charge. When we cross, drop, reduce with that, if we cross and drop, we end up with the X with a 4 and the Y has a 2. And then we have to reduce, we have to divide those numbers by the same value to get them to be the same ratio but smaller. And 4 and 2 can both be divided by 2. So 4 divided by 2 is 2, 2 divided by 2 is 1, but we don't write ones. So when we cross, drop, reduce our X +2 and our Y -4, we end up with the formula X2Y. That's really all we got to do. Find symbols, charges, then cross, drop, reduce. So if we go to the next page to work out some examples, I would encourage you to write your symbols and charges over the top of the element's name. This isn't really part of our answer, it's just part of the work that we're doing to get the answer. You really don't have to actually show the cross, drop, reduce. Like drawing arrows tends to cover things up and gets messy. But at the very least, being able to see the symbols and charges so you know you can visually kind of flip it in your brain to get that final formula. I'd encourage you to do that. It's not required. All I need is the final formula. So potassium and chloride getting together. Remember, chloride is just chlorine in a compound, so we're never going to find chloride on the periodic table, but it's almost the same as chlorine. It's not a typo though. And here, because we have that +1 and -1 charge, we can cross those, drop the sign, we end up with K1Cl1, but that just turns into KCl. We don't write our ones. Aluminum oxide. Aluminum is Al. It has a +3 charge. Oxide is oxygen. It has a -2 charge. And when we put it all together, if we cross, drop, reduce, bringing our 2 over and our 3 over, dropping those signs, we end up with Al2O3. For lithium sulfide, we've got lithium and sulfur. Lithium is a +1, sulfur is a -2. So if we cross, drop, reduce, bring the 2 over onto the lithium, And then 1 technically would come over onto the sulfur, but we don't write 1s. So Li2S is our final formula. For calcium oxide, we got our symbols and our charges, +2 and -2. And here, sure, we could cross and drop, make it Ca2O2, but then both of those 2's are going to reduce out, just like with our +3 and -3. But if we know the 2 and the 2 are just going to reduce out, if we can kind of see that coming, then we don't even really need to cross and drop here. It's just going to be CaO. And that's something that I do anytime that I notice that these charges are equal and opposite, whether it's a +3 and a -3, +2, -2, or the +1, -1 from over here. Anytime those charges are equal and opposite, we're just going to end up with one of each coming together into our compound. So next we have strontium bromide, strontium and bromine coming together. Strontium's in that second column, so it has a +2 charge. Bromine is a -1. So when we cross, drop, reduce, we end up with SrBr2. And then barium phosphide, barium and phosphorus, +2 and -3. When we cross, drop, reduce, switching those over, Ba3P2 is our final formula. So hopefully that's not too bad. You just have to find your symbols and your charges, but then you cross, drop, reduce every single time. Now, there are actually 2 different kind of variations of ionic compounds that we're going to talk about next, and we're still going to be crossing, dropping, and reducing with them. It's just kind of where we get our charges is going to be a little bit different. And the first variant are what we call transition metals, because like I pointed out before, we got a lot of transition metals that have multiple charges from underneath that staircase all the way over to that second column. They can have multiple charges. That doesn't mean they can't form ionic compounds. It just means we don't know what charge they have when they get into an ionic compound. And the way we figure it out, if we have one of those transition metals that has more than one charge, the name is going to have a Roman numeral in it to show us what that charge is. So when we look at this first example, copper 1 bromide, we find our symbols. Copper is Cu, bromide is Br. Bromide's charge is a -1 according to the periodic table, but we wouldn't really know copper's charge. It can be lots of different things. We don't know according to the periodic table, but that's why we have our Roman numeral 1 here. That tells us that this is going to be a +1 charge on the copper. And from there, cross-dropping and reducing is simple. It's just CuBr, because it's a +1 and a -1 together. For this next one, when we have tin 3 bromide, tin is Sn. We've got that same bromide as before. This is a -1. This is a +3, because it has a 3 here. It doesn't have a positive sign. Metals are always going to be positive though. And it really doesn't matter in the long run because we're about to be dropping that plus sign anyway when we cross, drop, reduce. But that just becomes SnBr3. Everything about our formula writing is the same. We still find symbols, charges, cross, drop, reduce. It's just going to be that our charge for that transition metal comes from the Roman numeral instead of from the periodic table. So with this copper 2 fluoride, this is going to become CuF2. Now you'll notice aluminum bromide doesn't have a Roman numeral. Even though Al is a transition metal, it is one of the few that has a set charge. There are 3 of them: aluminum, zinc, and silver. Aluminum is always a +3, zinc is always a +2, and silver is always a +1. And let's take a second to add that to our periodic table too. You'll notice that these 3 elements are kind of right next to each other in this kind of staircase area. Right underneath the staircase we have aluminum with its +3 charge, and it actually follows the rule that boron would say for the rest of its column. Gallium, indium, and thallium don't necessarily follow that rule. But aluminum is an exception that it does follow the rule of boron's column. And then you can kind of envision this as a staircase. Stepping down to the left, we have zinc, and its charge steps down to +2. And stepping down to silver, silver is a +1. So on top of these positive 1, 2, 3s and negative 1, 2, 3s from the rest of the periodic table, This is another 1, 2, 3 we need to remember, or 3, 2, 1 as we step down. These are also elements. You need to know their charges for our test. You've got to be familiar enough with them to use them when we need them. So coming back over to our practice problems, aluminum bromide, we do not need their Roman numeral to know that aluminum is a +3. So when it gets with that bromine, we end up with AlBr3. Antimony is a weird one. It's over there underneath the staircase. Sb is its symbol. It's getting with sulfur, and because we have that V there, that is a +5. With sulfur is -2, is going to turn into Sb2S5. And then lead nitride, or lead-4 nitride, tells us that lead is a +4 charge. Nitride is a -3, so when we cross-drop reduce, that becomes Pb3N4. And I normally write this a little bit later in the notes when we start having to come up with and write out these Roman numerals, but I guess it would help here. In case you weren't familiar, 1 in Roman numerals is just 1 line. 2 is 2 lines. 3 is 3 lines. 4, like we just saw down below, is IV, which makes a little more sense once you know and remember or realize that V is 5. So when we have IV here, that's 1 before 5. And then when we get to 6, it's VI, 1 after 5. That's about as far as we're going to need to go there. But it could be worth writing down just so that you can look over those and be confident in what that charge is. Now, our next variation of our ionic compounds and writing their formulas are what we call polyatomic ionic compounds. And atomic is just talking about atoms, and that prefix poly means many or multiple. So if we look at this formula for our ionic compound, this polyatomic ionic compound, it has many atoms together. All the rest of our compounds we've been writing formulas for only had 2 elements. These are going to have 3 or more elements all together in the same compound. And we're still only going to have 2 names for our compound. So there has to be some sets of special names for 2 or more elements when they come together. And that special list with all those special names for our polyatomic ions is right here in your notes. It's also on the back of your periodic table. If you flip it over, there's 3 sections on the back of your periodic table, and at the very far left is the same list of our polyatomic ions. So you do not have to memorize these. You just need to know when to flip your periodic table over to use this list. And if you notice in that list, most of these names like acetate, carbonate, chlorate, chlorite, chromate, dichromate, nitrate, nitrite, most of these names end in either ate or ite. All right, names here. So if you see something like calcium phosphate, that's what we're looking down here. Seeing that ate ending at the end of phosphate tells us that that's a special PO4 group. We flip over, find that in our list. That's PO4 with a -3 charge. If it was phosphide with that ide ending, then that's just normal old phosphorus. So anytime you see ate or ite, that's going to be one of our special groups. There are technically 3 groups that don't end in ate or ite, and that's ammonium, cyanide, and hydroxide. And unfortunately, there's not much of a special way to remember that those are polyatomics. Hydroxide kind of sounds like a polyatomic because it has that hydra for hydrogen and ox for oxygen, and that's all it is an OH group, oxygen and hydrogen together. But just like with elements, if you're in the middle of a test and you're looking and you're asking, like, ask me if you can't find something. And if you ask me, Miss, where is ammonium on the periodic table? I can't find that element. I'll flip your periodic table over for you and point out that ammonium is not an element, it's one of our special groups. So I can always help you find elements or help you find those polyatomics. But for most of them, just look for that ate or ite ending, and that will tell you that you need to flip over and find it on the back. And when we cross-drop reduce, the process is still the same. We find our symbols and charges, so calcium has a +2 charge, and phosphate has a -3 charge. And what you need to keep in mind is that those charges are the only part that is going to move or change. We're not going to move the 4. The 4 is part of the phosphate group. It's not the charge. The charge is always in that top right corner. So the charge is the only thing that we're going to cross, drop, or reduce. So we're not going to try and reduce the 4 with anything else. And so if we cross those over, the 3 comes over onto the calcium, the 2 comes over onto the phosphate. The only other thing that really is kind of special about these polyatomics is that when we put a number, when we cross a number over onto one of our polyatomics, to keep it from looking like here, you notice this almost looks like it has 42 oxygens here, not 2 phosphate groups, which is what we're trying to do here. We have to put that special group in parentheses. Everything the way it was written on the periodic table, except for the charge, because the charge is now moved, goes in parentheses. Whichever number we're trying to cross over onto it goes outside the parentheses. And that way we end up with a formula that looks like this final version here, where we have 2 phosphate groups, not just 42 oxygens and a phosphorus sitting there. So cross, drop, reduce. Remember to only be moving and changing the charges, and put parentheses around any polyatomics to protect it from that extra number, only if you have to add an extra number to it. So let's go ahead and do a couple examples here and get a little more comfortable with these polyatomics. So as I'm reading through, we're still going to start with symbols and charges. Potassium is K with a +1 charge. Carbonate is not just plain old carbon. That is one of our special groups on the back. It's CO3 with a -2 charge. And if we're going to cross, drop, reduce our charges with each other, the 2 is crossing over onto our K, and then the 1 technically could cross over onto the CO3, but since we don't write 1s, we can just write CO3. And we don't need to add parentheses here because we're not adding any numbers to that special group, so we don't need to protect it from anything. It's just carbonate sitting there at the end. So K2CO3. This next one is one of those tricky ones that is not ending with ate or ite. Ammonium is NH4 on the periodic, on the back, on that polyatomic list. And phosphate is PO4 with a -3 charge. So we've got a lot of numbers here, but the only ones moving or changing, the only ones we're going to be crossing, dropping, and reducing are the 1 and the 3. And so we're going to bring that 3 over onto the ammonium. So if we're going to need 3 ammoniums, we need to put that ammonium in parentheses with the 3 on the outside. And then we're just going to need 1 phosphate. The 1 from the ammonium comes over to tell us how many phosphates we need. So we just write 1 PO4, no parentheses necessary. Along with these polyatomics, we can still have transition metals there. So just putting all of these skills together, chromium 2 nitrite. Chromium is Cr with a +2 charge. Nitrite, careful, that's not nitrate, so nitrite is NO2 with a -1 charge. And once we cross, drop, reduce, that 2 from the chromium is going to cross over onto our nitrite. So we've got to put it in parentheses there. Same kind of thing happens with our mercury 2 acetate. Mercury has a +2 charge. Acetate is there at the top of our polyatomic list. It's the biggest, craziest looking polyatomic, C2H3O2. But don't worry about all those extra numbers. They're just going to go inside our parentheses. They're just going to stay the same. It's only the charge, that -1 charge, that we're going to be crossing, dropping, and reducing. So this just becomes Hg acetate in parentheses with mercury's +2 charge crossed over onto it. So for these next 2, we've got calcium with its +2 charge, and hydroxide, another one of those that doesn't end in ate or ite, but it even sounds like hydrogen and oxygen together. It is on the back of that periodic table in our polyatomic list. And here we've just got to remember to put that hydroxide in parentheses as we cross the 2 from the calcium over onto it. And we see our hydroxide group again with our antimony 5 hydroxide. So hydroxide is still a -1. When we cross-drop reduce, antimony's 5 crosses over onto our OH. So now that we've gone through all of our different variations of our formulas that we can write, I want you to practice writing formulas, but only formulas. So turn to page 9 and 10 and skip part 1 for now. Those already have formulas written. I am about to go over how to write names, but I'm going to do that in a separate section. I want you to do a little bit of practice writing some formulas. So part 2 and part 4 are all formula writing. Part 5 is a little bit of mixed up formulas and names, but anything where you already have a name, you can write the formula. So I've highlighted those here for you. If you haven't already tried some of these practice problems, I'd really encourage you to do some of those. If you need to check any of your answers, let me know. Sorry about that, but that seems like a good place to pause this, and we'll come back to doing some names in our next chunk.